We're Team 1004, doing problem C, dog cannot catch. We are here for you, Fritz. I'm Connor Talley from Kennesaw State University.
Hi, my name is Schwenck from Kennesaw State University.
Hi, my name is Yusuf Tekes and I'm from Innovation Academy High School. The owner throwing an object or food to his dog Fritz is considered a two-dimensional projectile motion with an assumption that the thrown object is a particle with a mass of m. The equations of motion of the particle along the horizontal and the vertical axis can be obtained using Newton's laws of motion. Here, theta is the attack angle in degrees, v sub 0 is the initial speed in meters per second, and y sub 0 is the initial height of the mass. When the object is following a projectile motion, the only force acting on the particle is the drag force, which is proportional to the velocity of the object. The velocity vector always points to the right side during motion, and since the drag force acts as an opposing force, it points to the left side. The equation motion referring to the Newton's laws of motion is mx double dot plus bx double dot is equal to 0, resulting in a second-order linear homogeneous differential equation. Starting with a trivial solution such that assuming e to the rt is a solution to the problem and taking derivatives and substituting it into the main equation, we find the general solution as x of t is equal to c1 plus c2 e to the negative bt over m. For the particular solution, we will refer to the initial conditions where the initial position is 0 and the initial velocity in the horizontal direction is v sub 0 cosine theta, and find the particular solution as in equation 1. The forces acting on the particle while it follows a projectile motion in the vertical axis are the gravitational and drag forces, which are both resisting forces. Setting the Newton's laws of motion using the force magnitudes and their directions, we find the general equation as my double dot plus by dot is equal to negative mg. This results in a second-order linear but not homogeneous equation, since the right side of the equation is equal to a constant but not 0. The solution to the problem is the combination of the homogeneous and particular solutions. While solving for the homogeneous solution, we repeat the same steps as in the horizontal trajectory calculations and find it as hx of t is equal to c1 plus c2 e to the negative bt over m. Since the right side is a constant but also missing the y of t term on its left side of the equation, the particular solution is selected as a second-order polynomial with coefficients of k1 and k2. The general solution becomes y of t is equal to c1 plus c2 e to the negative bt over m minus mgt over b. Using the initial conditions, including the initial velocity, attached angle, and the initial height, the final solution that gives us the vertical components of the particle is as shown in equation 2.
We begin the analysis of our differential equation system by looking at the trajectory of the particle as it moves through both space and time. Using equations 1 and 2 below, where equation 1 shows the x position with respect to time and equation 2 shows the y position with respect to time, as well as MATLAB's live editor, we are able to plot a curve that shows the projectile motion of the particle. We vary with respect to time, and we are able to obtain different x and y positions as the particle moves through time. This is then plotted in the curve as shown in the figure below. Next, we look at Fritz's motion from a fixed position. This MATLAB graph and code shows you how Fritz's position affects things, as well as certain different portions of Fritz's body and Fritz's movement of its body, and what we have to take into account when we're solving our differential equations. For this, we are able to look at the fact that Fritz jumps up by 50 centimeters, can rotate his neck by 75 degrees, and open his mouth by 45 degrees. We display another projectile motion curve as an object is thrown at 3 meters per second at a 20-degree angle of attack, and we show roughly with green and red lines where Fritz's mouth would be in this path for Fritz to catch the object. After looking at Fritz's characteristics, we now have to know where should Fritz stand to be able to catch the particle. So we start off with looking at the angle of attack changes instead of varying the velocities. We can see with this graph that when we vary the angle of attack, it shows a line in an area where most of the particles follow. The higher the particle is thrown, the further spread apart it is, and the lower it's thrown, the more clumped together those angles of attack are. This shows that if you want Fritz to catch the object, you would have better using a lower angle of attack or lower elevation of throw. However, if you don't want Fritz to catch the object, throwing it more close to straight up in the air would be better, as it's less likely to clump up with other objects thrown at different attack angles. This just makes it more difficult for Fritz to actually be able to catch the said object. Now that we looked at Fritz's positioning, we will go more in depth on when Fritz should be able to jump to catch the object. Using a jumping speed of 3 meters per second and knowing that Fritz can jump 50 centimeters high, we're able to calculate roughly when Fritz should time his jump to be able to catch the object. In the top graph to the right, you see a red dot denoted where the particle is when Fritz should jump. You see that the higher up it's thrown, the more time Fritz has to jump, and the later that dot shows up in the curve. However, when we only vary the angle of attack from 30 to 40 degrees, those dots are much more clumped together. The blue and purple lines on the bottom and upper graphs respectively denotes where Fritz is standing when Fritz jumps. This shows that if you throw it at an angle of attack from 30 to 40 degrees, the timing of Fritz's jump would be very similar. This shows a great way to train Fritz to be able to catch these objects. Lastly, in our analysis, we want to look at the effect the shape has on the drag, or the effect the drag has on the overall particle's displacement. In the graph, we plotted multiple different objects with different shapes, such as a cylindrical shaped meat or a spherical shaped apple. You can see, even with different sizes, masses, shapes, and even coefficient of drags, that the particle's actual shape of its motion changes very slightly. In fact, you can't even see the change. This shows that the drag force has very little effect on the motion for this particular example. However, depending on the orientation of the object you throw it in, this effect could vary. We now start to look at our Simulink code that helps us create other mathematical models to help display this relationship. In one of them, as shown here, we actually have a Simulink map of our differential equation rather than the physical equations that we solved ourselves. This is a much easier way to obtain the same result of positionings for both x and y directions. Going in more depth into our MATLAB Simscape simulations, you can see on the right there is the general system, which comprises of calculation subsystems as seen previously, as well as a visualization subsystem and a graphing subsystem. And the picture to the left shows a detailed breakdown of our visualization subsystem. While looking complex, this is what can actually help us animate the idea of Fritz catching an object. Lastly, here's an animation or video made using the Simulink model seen previously. This shows our approximation of Fritz catching a pizza in his mouth. This shows that using a lot of our equations, not only is it possible, but it's very easy for a mathematical model to predict whether or not Fritz should be able to catch the object. That is the end of this presentation. Thank you so much for watching.